Welcome. Today we're looking at why standard models often fall short of economic reality. In a theoretical OLS model, we assume a simple causal path from education to wage. However, the real world is more complex. Unobserved factors like ability act as confounders, influencing both the level of education attained and the resulting wage. This creates a correlation between our predictor and the error term, leading to biased and inconsistent estimates. This is what we call the reality gap. To bridge this gap, we use extended regression models, or ERMs, which allow us to model these complications jointly. This slide provides a high-level overview of the Extended Regression Model, or ERM, framework in Stata 18 and 19. At its center is the ERM core, which integrates seamlessly with panel data through XT commands. The framework is designed to handle three major economic challenges simultaneously. First, endogenous covariance, where unobserved confounders like ability affect predictors such as education. Second, selection bias, which occurs when outcomes like wages are only observed for a nonrandom subset, such as those currently employed. Third, treatment assignment, which accounts for the nonrandom assignment of individuals into groups, like a job training program. Finally, notice at the bottom that the ERM framework is highly versatile, supporting continuous, binary, ordinal, and interval-censored outcomes. Choosing the correct extended regression model command is straightforward once you identify the nature of your dependent variable. This decision map provides a clear path. For continuous outcomes, like income, you'll use eregress or xteregress if you're working with panel data. If your outcome is binary, such as a yes or no decision, eprobit is the standard choice. For ordered categorical data, like survey rankings of 1, 2, or 3, we use eoprobit. Finally, for interval or censored data, such as wage brackets, eintreg is the appropriate command. The real power of this framework, as shown in the code tip, is its uniform syntax. Regardless of which main command you choose, the core options for handling endogeneity, selection, and treatment remains identical. This consistency allows you to easily transition between different types of outcomes without needing to learn entirely new syntax structures. This slide serves as a Rosetta Stone, bridging the gap between familiar, isolated Stata commands and the unified extended regression model framework. As shown in the table, traditional commands for instrumental variables, eregress, selection bias, Heckman, and endogenous treatment, eregress, are all consolidated under the eregress command, using specific options like endogenous's, select, and entreat. For panel data, xteregress transitions to xteregress. The core advantage of this shift is that while traditional commands address problems in isolation, ERMs can handle them all simultaneously. For instance, modeling endogeneity, selection, and random effects in a single estimation step. To understand the power of ERMs, we need to look under the hood at the mechanism of joint error estimation. Traditionally, we might try to solve problems like endogeneity using a two-stage process, but ERMs take a more integrated approach. They estimate the main equation and any auxiliary equations simultaneously, using maximum likelihood. The central player here is the correlation parameter, rho. It represents the link between the error terms of our equations. When rho is 0, our models are independent and standard OLS is perfectly valid. However, when unobserved factors create a correlation between these errors, rho becomes non-zero, leading to biased estimates in standard models. ERMs solve this by explicitly incorporating this correlation into the model structure, allowing us to clean the results and identify the true causal effect. ERMs require a recursive or one-way flow of causality, known as the triangularity assumption. This means the model cannot handle simultaneity, where the outcome and predictor affect each other at the same time. As shown in the left panel, causality must flow in one direction, such as z influencing x and x influencing y. This is a recursive structure.
In contrast, the right panel shows a feedback loop where X and Y affect each other instantly. ERMs cannot model this type of simultaneous causation. For instance, in a labor market model, we assume education affects wages, but current wages do not instantly change education levels within the same period. Ensuring this one-way flow is essential for the validity of the model. Next, let's explore how we interpret the coefficients from these models.
Now, let's discuss how to interpret the results from an extended regression model. The coefficients produced are structural parameters. Much like the camera lens in our visual, these models clean the bias generated by endogeneity, selection, or treatment assignment to focus on the true causal effect. The standard interpretation still applies. Holding other factors constant, a 1-unit change in X leads to a beta change in Y. What's powerful here is that this interpretation remains valid even when X is correlated with errors, assuming your instruments are valid. To calculate margins and find the true population effect, we use the average structural function, or ASF. The ASF effectively averages out the heterogeneity caused by endogeneity, allowing us to see the average effect across the entire population. This slide provides a visual breakdown of the syntax for an extended regression model command in Stata. The command is structured into 4 distinct parts. First is the main equation, which represents the primary linear regression of wage on experience. Second is the endogeneity option, allowing us to handle unobserved confounders by instrumenting education with mother's education. Third is the selection option, which manages sample selection bias, for example, when wages are only observed for those currently working. Fourth is the treatment option, used to model treatment assignment, such as union membership. The key takeaway is the modular nature of the syntax. Users can mix and match these options as needed, and there is no requirement to use all of them in every model. This slide outlines advanced settings for ERM models. For instance, the probit and eprobit suboptions are used for binary or ordinal endogenous predictors. The no main option handles instruments that do not appear in the main outcome equation. Lastly, pole correlation allows for heteroscedasticity by permitting error correlations to differ between treatment groups. These options allow you to tailor the model to your specific data requirements. For panel data, always start with the xtset command to define your cross-sectional and time identifiers. Identify valid instruments Z that correlate with your endogenous X, but not with the error epsilon. For selection models, ensure you have a binary variable where 1 represents an observed outcome. If using interval regression, double-check that your lower and upper bound variables are correctly formatted. Using xtset to prepare a panel of 500 individuals observed over 10 years before running xteregress, let's apply these concepts to a real-world scenario. In this practice scenario, we aim to estimate the causal effect of education on wage using the dataset wagedata.dta. This analysis is complicated by 2 factors. First, endogeneity arises because high-ability individuals often obtain more education and earn higher wages, leading OLS to overestimate the return. We address this by using mother's education as an instrument for education. Second, selection bias occurs because wages are only observed for those currently employed. To solve this, we model the probability of working as predicted by family size. The diagram visually represents these paths. Mother's education influences education, which in turn affects wage, while family size influences the working selection filter that determines whether a wage is observed. Now, let's move into the practical application in Stata. In this step, we'll execute the unified analysis using the eregress command. First, we start by loading our dataset, wage data. The power of the ERM framework lies in its modularity. As you can see in the command window, we're not running separate steps. Instead, we combine the main regression for wages with sub-options that handle our specific econometric issues. We include the endogenous option to model education, using mother's education as an instrument. At the same time, we add the select option to account for selection bias, specifically that we only observe wages for those who are currently working, modeled here by age and family size.
By using the triple / syntax, we keep the command clean and readable in our do files. This single execution allows Stata to estimate all these relationships jointly, ensuring consistent and efficient results. Once the model is run, we need to focus on the most critical part of the output, the significance of the error correlations, often referred to as the smoking gun. Look closely at the bottom of the table, highlighted in the red box. We are checking if the correlation coefficients, represented by rho, are statistically significant, meaning the p-value is less than 0.05. In this case, we have a significant correlation of 0.45 between education and wage errors, p less than 0.01, and negative 0.12 for working and wage errors, p less than 0.05. This confirms that both endogeneity and selection bias were present in our data. Therefore, the ERM correction was absolutely necessary to obtain valid structural estimates and move beyond mere correlations to true causal effects.
Once the model has converged, we move to the final step, interpreting the real-world impact. We can calculate the average treatment effect using the estat teffects command. To make these results intuitive, we use margins and margins plot. In our do file, we've specified education levels from 10 to 20 years. The resulting graph on the right displays the structural relationship between education and wage. Notice the shaded area, which represents the confidence intervals. Because we used the ERM framework, this upward trend isn't just a simple correlation. It's a structural effect that accounts for unobserved factors like ability and self-selection into college. Let's wrap up by summarizing the key advantages of this approach. To wrap up, let's revisit the key strengths of the extended regression model framework. First, its unified power comes from integrating endogeneity, selection, and treatment effects into one seamless model. Second, it utilizes joint estimation, which directly addresses bias by modeling the error correlation coefficient, rho. Third, the addition of panel support via xt commands means you can now apply these advanced techniques to longitudinal datasets. For those ready to dive deeper, I've provided links to the official Stata ERM manual via the QR code. You can also access immediate documentation within Stata by typing help eregress or help xteregress into the command window.